And so today we're going to look at another way of calculating it. As I scroll through here, you'll see this example they did. Again, this is what we looked at last time, where they're using the Gibbs free energy equation. They're using this table of delta H of formation and absolute entropy values. And then these formulas that we talked about last time, where you have this summation symbol, which comes from math. It's a math symbol. That means that you're adding up all of the terms, and the little p here refers to products. There. Oops. So you have the summation over products first, and then you have the summation over reactants after that. Those products minus reactants with the coefficients also in there. And the same thing for the delta S formula here. Products minus reactants. And then in the example, you can see that from the chemical equation, let's go up here for a second. The chemical equation has a half in front of the oxygen. So when you apply this formula, you have to multiply those values from the tables by whatever the coefficients are. So there's a 1 in front of the SO2 and the SO3, but there's a half in front of oxygen. So when you go down here to apply the formula, you have to put that half in here when you're doing entropy, because the entropy of oxygen is non-zero. So that's where this 1/2 here comes from, the coefficient in that chemical equation, the way that it's written. Okay. Any questions so far on that? That's kind of a review of what we did last time. So you have these two equations. So once you get these two values from those equations, that's the delta H0, that's the delta S0, then you got to put them in the Gibbs free energy equation, and that's done right down here. So here's the Gibbs free energy equation right there. They have the delta H is a negative value. Remember, it was minus 98.9 kilojoules that they calculated, but the delta S was minus 94 joules. So the only way that you can do that and make the units consistent is to convert them both to the same units. So here they choose to convert the delta H to joules by multiplying by this 10 to the third in there. So you got to be a little careful about units when you use this Gibbs free energy equation. It's supposed to be an arrow right there. And then also you multiply by the temperature, and the temperature has to be in Kelvin. So that's this other term here. Okay, so those are all the terms there. And then they do that subtraction, which ends up actually being an addition. Your negative here and the negative here cancel. So you get a negative number and then minus another negative number. It still comes out overall negative, because this product is still less than the delta H once you convert both to joules. Okay, so that's doing the calculation with Gibbs free energy equation. They give you a practice problem here doing the same thing, but with this formula, so I won't work through that. But you can try that one if you want. The answer to these practice problems, I think, are in the back of the chapter. Okay, so this next example they do is similar to the first one, but they have to make an assumption about the way you can use Gibbs free energy equation quantities. when you pull them from the table, they're only valid exactly at 25 degrees centigrade. That's what these are, only at 25 degrees centigrade, because that's what the table is created for. But sometimes you might want to calculate delta G at a temperature other than 25 degrees centigrade. Well, you can do that, but if you use the Gibbs free energy equation, which is right here, if you use this equation and you use it with the tables from the book, or from a published set of thermodynamic values, if you use that, that's only strictly completely valid also at 25 degrees centigrade. So what they do here is they make an approximation that the temperature dependence of delta H and delta S is fairly insensitive. So in other words, the values of delta H and delta S don't change much with temperature. So if you can assume that, then you can make an approximation that this would still be true even if you're not at 25 degrees. Any temperature you can make an assumption that those are still valid numbers. Now, in this particular example, let's see what they did. Did they give you those values or not? No. See, they're doing the same thing. They're doing an estimation. That's why it says estimate the value of delta G at 125. So 125 certainly isn't 25. It's much higher than that. But that assumption, that's valid as long as you're not too far away from 25 degrees. So certainly within plus or minus 100 degrees of that. That would be. So really, when they solve this problem, they should be saying that this is approximate in the equation. They really should say that the delta G0 only approximately equals the delta H minus T delta S at any temperature. So the temperature that they put in here now is not 298, it's 398. Yeah, 398, because 125 would be 398 Kelvin. And that's the only difference, is that number between whether you were doing this at 25 degrees or whether you're doing it at 125, is that you're changing that value right there. Let me get that. So even though you're kind of limited by values from the table being at 25 degrees, if you need delta G0 at some temperature other than 25, it's a good assumption that you can still use those values for delta H and delta S, even at that other temperature. Now, that's important because there's another way of calculating delta G0, which you can only use if you're at 25 degrees. And that's if you have tables of delta G0. So let me scroll down a little bit, and that's what they get to next. Calculating delta G0 with tabulated values. Tabulated values, okay. So, and just like with delta H and delta S, you can use a formula that has products minus reactants. It looks Right here is formula 1912. Okay, so this formula right here, this looks just like the delta H and the delta S formula with our little sigma values there. Except now you're using delta G formation instead of delta H formation, for example. Okay, so they go through an example of doing that as well. Now this table 19.3, this is so this is just another table that shows thermodynamic values, but it's only delta G. There are tables in the back of the book that show everything. They kind of summarize all three of these. So you have all these different elements with their delta G information values. You can look them all up. One thing to notice here is that, again, just like delta H values of formation, when you're dealing with elements like hydrogen, oxygen, nitrogen in their standard state, in other words, the way they would normally appear in their most stable form, the delta G of formation values are also 0, just like with delta H. Now, graphite is the most stable form of carbon. So if you have carbon as diamond, that delta H of formation value is not 0. They do an example here of combustion of methane to produce carbon dioxide and water plus ozone. Oh, okay. This is not a typical combustion reaction because they're showing information of ozone here. Anyway, to do you could calculate the delta G of this from the tables. If you had a list of delta G of formation of methane, of carbon dioxide, of water, and of ozone, oxygen would have a 0 delta G of formation. So they gather all that information down here, and then they plug it into this summation formula where you have the reactants minus the products, do the calculation. The only thing on here, they're actually trying to get you to calculate, your unknown on this actually is the delta G of formation of carbon dioxide. Because they give you the did they give you the delta G of the reaction? Use a standard no. I don't know why they don't put a number. Oh, I'm sorry. They do have all numbers in here. No, I'm sorry. I was looking at something. So yeah, just they're just showing you the delta G symbols here and then putting the numbers in. And of course, they have the coefficients along with these. So you have your 2 here. So who can tell me why there's a 2 right there in front of the minus 228?
There's 2 moles.
In?
There's 2 moles.
In what?
H2O.
In the chemical equation up here. Yeah.
Yeah, H2O.
I know that's what you meant, but so yeah, in front of the H2O, there's a 2.
Right.
In the chemical reaction, in the balanced chemical equation.
Right, and then ozone has 4, so the coefficient's going to be 4.
Exactly.
In the 8 for O2, but O2 is 0 anyway. So.
Yeah, so that's pretty straightforward to use, but you do have to remember that this delta G0 you're calculating is only at 25 degrees. There's no temperature in this formula anyway. Really only calculating the delta G when both reactants and products are 1 molar concentration or 1 atmosphere pressure. So if you go back up to the chemical equation now, these are all gases anyway, so it means that each one of these gases is at a partial pressure of 1 atmosphere. So it's a pretty restrictive number that you're calculating.